Hello everyone, so in this video we are going to discuss about discrete time Fourier transform. In the previous videos we have discussed the properties of continuous time Fourier transform. Now discrete time Fourier transform is analogous to continuous time Fourier transform case with some significant differences, and we will understand as we improve in this lecture. And we have already seen how we developed the formula for Fourier transform using the Fourier series coefficients. So we have first made a signal in which we have represented in terms of the Fourier series representation, and then we started to increase the period of that periodic signal, and we have seen that how we can represent the aperiodic signal in terms of Fourier transform. So we will use the same analogy here also. So suppose we have a signal xn, and the representation of xn, so it's an arbitrary signal, so it doesn't have any pattern. So I'm just giving some random pattern. So suppose this is your signal xn. So we have an signal xn which is varying from suppose some minus n1 to n2, and for all other values it is having a 0 value. So this is your n. So this signal has some values in between the range minus n1 to n2. So this is an aperiodic signal. So as you can say, this is aperiodic. Now we have to construct a periodic signal from this aperiodic signal. So what we'll do, we'll repeat this signal for a period of suppose a value n. So this is your aperiodic signal. We will repeat the same signal. So we have this signal as our xn, which is varying from minus n1 to n2. Now we'll repeat the same signal for a period of n. So again this range is n2 minus of minus n1, so that will be n2 plus n1, and again for the case of minus n, it will be represented like this, and so on. So now what we did, we constructed, so from this aperiodic signal we constructed a periodic signal of period capital N. So we have just repeated the signal xn for every n value, and we name it as x dash n. So x dash n and xn has a similarity in the period represented by this range. So minus n1 to n2, it is same as xn, otherwise x dash n is a repeated version of this xn. So now we will try to write the Fourier series for this periodic signal. So we have the formula for Fourier series already. So we can write x dash n as summation k is equals to n. So this is the period n, ak e raised to the power jk 2 pi by capital N multiplied with small n. And we also know that for the coefficient, what we can write 1 over n summation k equal to n x dash n e raised to the power minus j k 2 pi by n multiplied with small n. So now we can replace this value as, so ak can be written as 1 over n. Now we know that the signal has values only in the range minus n1 to n2, so we can write it as xn, and in that range x dash n is having the same form as xn. So if we'll consider this signal for this period only, so minus n1 to n2, it is same as xn. So we can write x dash n as xn in the period minus n1 to n2. So when we replace this range as minus n1 to n2, we can have xn e raised to the power minus jk 2 pi by capital N into small n, and that can be written as summation n equal to minus infinity to infinity x of n e raised to the power jk 2 pi n multiplied with 7. These two values will be same. because xn is taking values into minus n1 to n2, and if range is changed to minus infinity to infinity, that doesn't change the value of this summation. So now next what we can write, we can have a representation which is x e raised to the power j omega as summation n is equals to minus infinity to infinity xn e raised to the power minus j omega n. So here what we have did, so ak can be represented as, so from, if we replace this in this, what we'll get ak as 1 over n x of e raised to the power j omega not k, and here omega naught is given by 2 pi by n. So now how we can write x dash n? We can write x dash n as summation k over n 1 over n x e raised to the power j k omega naught multiplied with e raised to the power j k omega naught n. And now that will be omega naught. And now as n tends to infinity, omega naught will tend to 0. So here this value can be replaced with d omega. So now it will be changed to integral. So summation will change to integral, and xn will, if n tends to infinity, it means that period is increased to infinite. So xn will, x dash n will approach to xn. So we'll write xn as 1 over 2 pi summation over 2 pi x e raised to the power j omega e raised to the power j omega n d omega. So this can be directly inferred from this expression. And period is 2 pi, as we all know that for discrete time signal it will repeat itself after a period of 2 pi. So our period will be 2 pi. So, and the other form is x e raised to the power j omega, which we have already shown in this form, can be represented as xn e raised to the power minus j omega n. N is varying from minus infinity to plus infinity. So here these two expressions are very important, and they form the Fourier transform pair for discrete time signal. So in short form they are also called DTFT, as analogous to what we have said that continuous time Fourier transform is called CTFT. So these are the two expressions which we have seen that how we derived it from the Fourier series expression, as we have done in the continuous time case also. So now just to get the better understanding of these two formula, we will try to solve some examples. So we will start with our first example. So now we will take an discrete time signal as a raised to the power n un, where mod a is less than 1. So we have the formula for our Fourier transform. So that is equivalent to n is equals to minus infinity to infinity x n e raised to the power minus j omega n. Now we'll replace x n with the given form. So that will be a n u n e raised to the power minus j omega n. And we all know that un is having a value only after n equal to 0. So this range will change to n equal to 0 to infinity a n e raised to the power minus j omega n. This can be equivalently represented as n is equals to 0, infinity, a raised to the power n. So we can write it in a collaborative form as a e raised to the power minus j omega whole power n. So now it is a geometric series, infinite geometric series, and we all know the formula for that. We can directly write it as 1 over 1 minus a e raised to the power minus j omega. So the Fourier transform of a raised to the power n un can be given as 1 over 1 minus a e raised to the power minus un with mod a less than 1. So this is the form, and this is very commonly used signal throughout this course, so you should remember this form. Now we'll solve for another common signal, discrete time signal. So that will be xn is equals to a raised to the power mod n, and again mod a is less than 1. So again we'll apply the formula for the Fourier transform of x e raised to the power j omega. That will be summation n is equals to minus infinity to infinity a mod n e raised to the power minus j omega n. So as we know that mod n is there, so we can split this integral in two ranges. For n is equals to minus infinity to minus 1, it will be a raised to the power minus n e raised to the power minus j omega n, plus n is equals to 0 to infinity a raised to the power n e raised to the power minus j omega. So these are the two form in which we can split this. So now for this case we can directly write it as n is equals to 0 to infinite a raised to the power n e raised to the power minus j omega n, and for this case we will replace n with minus of m. So what it will result? It will result in m is equals to 1 to infinity a e raised to the power j omega m. Now we'll again apply the geometric series formula. So for that what we'll get 1 over 1 minus a e raised to the power minus j omega plus a e raised to the power j omega divided by 1 minus a e raised to the power j omega. And when we rearrange and solve it, we'll get a simple form as 1 minus a square 1 minus 2a cos omega plus a square. So the Fourier transform of a raised to the power mod n is given by 1 minus a square by 1 minus 2a cos omega plus a square. And again the condition for a is mod a should be less than 1. And this is again a very important form, and it is also going to be used throughout this course. Now we'll solve the third and important form. So we have a discrete time signal as xn, which will take a value of 1, which is where n is varying from minus n1 to n1, and it will take a value of 0 for all other values. So can you link it with its continuous time case? So yeah, it is analogous to your square pulse. So here we have, so we can represent this signal as, so this signal is taking a value of 1 from minus n1 to n1. So this is your n1, and for all other value it is 0. So if you will see the envelope of the signal, you will see that it will be resembling the square wave in case of continuous time. So now we'll solve the Fourier transform for this kind of signal. So we have x e raised to the power j omega. So we know that for the interval of n varying from minus n1 to n1, the signal is taking a value of 1 e raised to the power minus j omega n, and for all other value it is 0. So the Fourier transform will come out to be sine of omega n1 plus 1 by 2 divided by sine omega 2. So you can directly solve. It is not a very hard problem to get this. I'll just give you a hint like how you can solve it. You have to just replace. So from this expression what we'll get summation n equal to minus n1 to n1 e raised to the power minus j omega n. So in this form just replace m as n plus n. So what will it will be? It will be changed to 0 to 2n e raised to the power minus j omega m minus n. So how we can write it? We can write it as 0 to 2n e raised to the power minus j omega m multiplied by e raised to the power plus j omega n, and that can be represented at e raised to the power plus j omega n summation 0 to 2n e raised to the power minus j omega n. So again, this is a geometric series, and you can write it is in the form of 1 minus e raised to power minus j omega 2n plus 1 minus e raised to power j omega multiplied with e raised to the power j omega n, and from this you can directly get this when we solve from using the Euler's forms. So this is a short derivation to understand like how we got this expression from this expression, and this is quite widely used form, so you have to remember this form. So suppose if a signal is varying from minus n1 to n1, you can directly say the Fourier transform is sine omega n1 plus 1 by 2 divided by sine omega 2. So this signal will resemble u as sinc function, but there is a quite difference. Like in continuous time case, what we have seen that the Fourier transform comes out to be a sinc function. So sinc function in continuous case was aperiodic, but here what you get, you get a periodic wave. So this will be a periodic wave. So this is the significant difference between the form of Fourier transform which we get in continuous time case and discrete time case. So they look analogous, but there is a significant difference in between them.